for the simple harmonic oscillator, the quantum oscillator. So just draw a line like this. Okay, so the Hamiltonian is very special here. This won't work for a general Hamiltonian. But we start out by writing the Hamiltonian for this problem, right? And we're in one dimension, it's important. So we're aiming to get the energy eigenvalues out. So this, you can write the Hamiltonian in this form, okay? Now, what we do is we scale to dimensionless quantities, because it makes the algebra a lot easier when we do that, okay? This is something we tend to do in physics quite a lot, actually. Okay, just give me a second. Right. So, I define G, the operator G, to be, I'm going to base it off of this, okay? Define it as the square root of m omega over h bar of whatever x is, okay? In fact, I'm not going to bother writing this as an operator, okay? We just understand that it is an operator. Of course, we'll have to be careful because it's not going to be commutative then, right? Okay, so we have G is this. Also, I define an epsilon of reduced energy, okay? So this right here is dimensionless, okay? And essentially what I'm doing here is I'm taking the ratio of E to h bar omega, okay? This right here is going to be a dimensionless quantity. Okay, we're going to be, this epsilon is the units of h bar omega, if you like. Okay, and then later on we're going to find that the raising operator takes epsilon of n, right? This is indexed by some n, takes it from that to epsilon plus 1, okay? And this makes sense because the energy is quantized by units of h bar omega. We'll find all of that. Okay. So, okay. Before I go any further, one can easily check that the Hamiltonian, right, can be written in terms of. In fact, I'll go through that in a second. Go through that now, actually. Okay. So I can, by doing this, right, the use of doing this is that I can write this in terms of a really simple form, just involving G. Okay. So. Okay, there's a factor, prefactor of half, multiplying everything. So what is this? This is going to be, so I take square on both sides. I get m omega, okay, m omega x squared is equal to h bar g squared. But then I have an extra factor of omega, so I have h bar omega g squared. So that's this, when I make the substitution. Okay, minus. So this right here, how do I convert from this to this? Well, d by dx is the same thing as taking dg by dx times d by dg as the chain rule. Okay, this right here is just this factor right here. Okay. Now, therefore, for the square of this, when I operate this twice, I'm going to get m omega over h bar squared d2 by dg squared, okay? Is that correct? Yes. Yep. Okay. Okay, this is d, yeah, so then I can bring this on the other side and get h bar squared over m omega d by dx. d2 by dx is this, okay? Well, let me multiply through by omega, okay? No, that's not right. Sorry, there's no square here. It's just this. Okay, so I multiply by omega, and then we multiply by h bar, and I get this. So I can substitute this into here like that. Yeah, I factored out the half, remember? This is h bar omega d2 by dg squared. Okay? So then, Hamiltonian is this. But remember, we're working with the reduced energies and all of that. So if I divide through by h bar omega, I call this my new Hamiltonian, the reduced Hamiltonian. I'll just abuse notation and just call this h again. And this is using that thing right here. Remember though, the energy eigenvalues, I'm going to label this by epsilon, at least to avoid just a little, just to try to at least make things a bit notationally clear. Okay, so we have this relationship, great. Then I define the raising operator. Be careful, there's a minus sign here. It's very important. It's a minus sign. And then I define the lowering operator by this. Be careful, there's a plus sign here. Yeah? But there's a root 2. Now, it's tempting to say, when I take a plus times a minus, I'm going to get the Hamiltonian back. But that's not true, okay? That's not true. Think about what you're doing. When you multiply these two out, yes, there's a difference of two squares, but they involve the cross terms, which you assume were 0, right? Which assume cancel out, but that's not true if it's not necessary. So, let me take a plus, a minus. This is going to be 1/2 of this, yes, sure, right? Then minus, okay, so, sorry, so these n terms are going to appear, but then it's going to be what? So it matches in the order in which I did this, so it's going to be g on the left, and minus g on the right. Okay? Now you'll notice that to be the commutator of g with dg. Okay? This is the commutator of g with dg. But we can simplify this. Okay? How do we simplify expressions involving commutators? We have to apply it to some psi. Okay? Because this thing right here is not d by dg of g. Right? What this term is you'll see in a second. So when I apply psi to this, then this applied to psi is d psi by dg, sure, then minus d by dg of g times psi. Okay? And when I expand this out, I get a term g, d psi, so it cancels that out, and then I get a minus psi. So this thing is minus psi, therefore the commutator, this commutator is -1. So, this thing right here, I can replace this as -1. Be careful, technically speaking, this is the minus the unit operator, okay? But I won't bother. Everything here are operators. But I'll just call this one, okay? Okay, so that's fine. Well, notice that this right here, I can split it up as the Hamiltonian, get the Hamiltonian back, right? And -1/2. So the Hamiltonian is a plus a minus plus 1/2. Okay? Alright. So, what now? Okay. So, at this stage, what I want to do is, I want to show, okay, turns out that if I take, this is called a plus for a reason, right? If I take this and I apply it to some un, right? Actually, that's not quite, okay, so, right, let me backtrack for a second, right? So, this un, okay. Alright, let's conceptually try to understand what the idea of a raising operator is, and then we're going to get to showing all of this being true, okay? Suppose that I have an eigenfunction of the Hamiltonian, okay? Right, that's crucial. I'm not saying that it's a eigenfunction of a plus or a minus or anything like that, okay? I take an eigenfunction of the Hamiltonian, un, okay? And that ink does not, that colour does not show very well, so I still want to stick with another colour because it's kind of looking ahead. So suppose that un is an eigenfunction of not a plus, not a minus, but of the Hamiltonian. Okay? So this will have some energy associated with it. Okay? So this is, let's say, the eigenvalue of this, the energy, so the eigenvalue of the Hamiltonian gives you energy, so let's say that the energy is epsilon n. Okay? un. Okay? I don't know yet that the energy is quantized or anything like that, okay? But I'm labeling this by n because I'm labeling, I'm indexing this by n as well. There's nothing right now saying, just from how I've written it, that things have to be discrete. In fact, let me forget about the label. Don't think I need the label n really there. Let me just call this u, okay? Okay. Alright. So here's the deal. I have a Hamiltonian acting on some eigenfunction, which I'll call u, and it spits out an energy eigenvalue epsilon, and then times u, okay? That's what it means for u to be an eigenvector of an eigenstate of H, the Hamiltonian. Okay, so what does the raising operator have anything to do with this? Well, we're going to show that if I take the raising operator and I apply it to u, right, this won't necessarily be some constant times u, okay? That's not true, okay? But what will happen is that this guy will send this u to some other state function, okay? But this new state function, right, a plus acting on u, is very, very special, okay? Because it turns out that if I take this thing turns out to still be an eigenstate of the Hamiltonian. Okay? It turns out to still be an eigenstate of the Hamiltonian, even though the u is not an eigenstate of a plus. Okay? So it turns out to be an eigenstate of this thing turns out to be the eigenstate of the Hamiltonian. So, and the eigenvalue turns out to be epsilon plus 1. Okay? So, what this is that I've taken my old eigenstate u, right, and it has some energy epsilon associated with it. I take it and I apply this raising operator to it. It sends me to a new eigenstate, right? It's a completely new eigenstate. But this eigenstate, it will send me to a new state, okay? So this u acting on it sends me to a new state function, right? New wave function, state function, whatever, right? But it turns out that this new state function is still actually an eigenfunction of H. And furthermore, the eigenvalue is now epsilon plus 1, okay? And this right here, tells you that this right here gives you the next, and if you can find what this guy is, right, then you have the eigenfunction, the state function for the next energy level up the ladder. Okay, it takes you from one rung to another, right? Because remember, this epsilon is the reduced energy, right? So this is all in units of h bar omega. Everything here is dimensionless. Okay. So let's show that this is true. Okay. Let's show that this is true. How do we do this? Well, there are several ways to do this. Sorry. But let me start with this. So this is pulling a, bunny out of a hat a little bit. Okay, I'm thinking about the most natural way to do this actually. So what's the most natural way to do this? Okay. So let me take, okay. So this is the way we tend to do it, okay? So let me take my u again, okay? Let me act on it with the Hamiltonian, right? This is an eigenfunction. What I'm looking for is I'm trying to get, at the very end, h bar a plus u, okay? So the journey, that takes me from this to this, we'll start with, let me apply a plus on the left, okay? Now it would be really lovely if I could just swap the order of this, and then I'd be pretty much done. I'd end up with this expression, but obviously I can't commute this, okay? But let's work with this, and let's try to play hide and seek and try to find this expression, okay? So we're going to have to bring the commutator in, okay? This will be take this, right, this is equal to that. Let's make the thing that we're looking for just appear out of thin air, okay? By adding by 0. So this thing right here we're looking for, this thing we're going to try to simplify. Factor this out. Okay? At the very end, we're going to bring whatever happens here to this side and then find what, to solve for what the Hamiltonian acting on whatever state function a plus takes u to. Okay? Right? Let's carry on. Well, what is this right here? So this right here is the commutator, and how can I simplify this? Well, I'm going to have to get my hands a bit dirty. Okay? Let me erase all of this. Well, not all of it. Let me erase this bit. Okay, so h we have an expression for, right? So this is a plus a minus plus a half a plus, right? Minus a plus a minus a plus minus a half a plus. Okay? All of this acting on u. Okay? So remember, to simplify a commutator, we wanna imagine it acting on something, right? So this thing right here is the commutator, and it's acting on some u. This is this, all acting on u. Jeez, how can we simplify this really nasty looking expression? Okay, so these two terms at least cancel. Okay, so I'm going to simplify this. It all comes down to figuring out what the heck we can do with all this. Let me bring a plus on this side, so why not? What is this? So this right here is the commutator of a plus with a minus. Okay? But we actually worked this out already, didn't we? Well, we worked out the commutator of g with dg, d by dg. Yeah? So this right here is 1 over square root 2 g minus d dg. And this. Now we can use the algebra of the commutators to simplify this expression easily. Okay. So what will we do? I need to get rid of something. I'll get rid of all this. Get rid of this. Okay. Well, I can factor out 1 over root 2 from both sides. This is bilinear, essentially. Right? Yeah, that's correct. It's it's bilinear, so we can bring this out. We get, so this right here simplifies the commutator g with g, which is 0, we know that, minus commutator of dg by g. In fact, I'll write it like this, plus plus g with the commutator dg, yep, and then finally plus minus dg with dg. So I'll immediately get rid of the things that are obviously 0. So this is obviously 0, this is obviously 0, okay, right? So what is this? Well, throw the minus sign out here. This thing right here, we've already seen. Let me actually have to quickly check this again. So this right here is 1. So we get minus 1 here. This thing right here is minus 1. So it's minus 2. So this whole thing simplifies to minus 2. Minus 2 times a half. This gives you minus a. So that's pretty straightforward. So this commutator right here simplifies to minus a plus. Okay? Okay, so that's not too bad. Okay. Okay, but what is I'm getting myself really muddled up right now. Okay, I need to further simplify this. Get that this is equal to. Sorry, what is this right here? Oh, sorry, I said that this is minus 1, sorry. So this entire thing is minus a plus u, right? So this thing right here is minus a plus u, right? So therefore, the commutator to this has to be the operator minus a plus, okay? So this thing right here is minus a plus. And this is plus h equal a plus u. Okay, now I send this to the other side and I get h plus epsilon a plus u, which is the expression that we've been seeking after all along. It's a plus factored. Do you want to do it that way? Yeah, sure. A plus into so this is a plus u plus a plus h bar u, but this right here is the reason why we did this. We started out with something that we know is an eigenstate. This is epsilon, right? So factoring all this out, you get a plus epsilon plus 1 u.